Yeah.
So, you notice I wrote that in big letters. We're starting something new. Officially. We're going to look at something called a function today. It's not going to look all that different from what you've seen in math before. Look very similar things, but you want to pay attention to the fine points. Once we get through discussing functions in the abstract, we're going to look at a lot of specific functions. Some you may have seen before, some you probably won't have. And it's important to know what we mean by a function. Some of the finer points will show up. I was riding the bus here today thinking about this, and sometimes in math, mathematicians are not, like Shakespeare. They're not great with words always, and sometimes they come up with something new and they just want to pick a name. Sometimes it's a good name, and it kind of fits the mathematical. I mean, you can make something completely up. Or you could use Latin prefixes and suffixes. But often they'll pick something that already has a meaning. Function has a meaning in English. It overlaps a little bit with what mathematicians are thinking of. The function of my arm is to wave around and do things. That's not what mathematicians think of the function as. But, you might think of a factory having a function. It takes in raw materials, and the output is some kind of consumer products. You do want to be careful in math when you see some word, and usually that word will give you some feeling for what it's about, but not always. So I think with function it's kind of half and half. You do want to be a little careful. So, before I get going, there's a homework 1.4, no name. This looks like your handwriting. You can come up and put your name on it if not. It'll remain a mystery. All right, so what is a function mathematically? Well, before I describe a function, I want to describe something even more general, which is a mapping. A mapping just says I have two sets, and I have some kind of objects in the sets. Let's make it simple, they're just numbers. And the mapping is just these two sets, and, well, you can think of it as just like lines being drawn between them. I'm just associating 1 and 4. I used wrong vocabulary here. What I'm describing is a relation. A relation is a mapping. But the thing about a relation is you could have, 1 going to 4 and 5, and you could have 3 going to 6 and 5, and multiple things go to 5. A relation is very general. It's just a totally general map where we associate, one set of objects with a bunch of other objects. What makes a relation a function is one rule which says, let me redo this. You can have one of these objects going to, one could go to 4 and 2 could go to 4. But each object in this set only goes to one value, or one other object. That's what makes this a function. So we have a name for this set here. This is called the domain. You've seen that before. But in this case, this is the domain of a function. It's not the domain of an expression. It's going to work very similarly, you're going to see in a minute. One important thing to know about functions is that people often mistake, you're not going to use the letter F to mean a function. People often mistakenly think the function is just this mapping. It's not just the mapping, it's the mapping and the domain. It's the whole thing. I guess we'll start over here. In particular, let's say I have a function. We're going to use this notation. This means the function on some independent variable. This comes from the domain. And we'll write something like this. Let's say f of x equals x squared. So what does this function look like over here? Well, approximately looks like 1 is going to go to 1, 2 is going to go to 4, 3 is going to go to 9. But it's important for me to indicate in some way, either by default or explicitly, what the domain I mean is. If I said x is the member of the real numbers, that's the default. I don't say, typically I mean all the real numbers. That means I can take any real number and plug this in, and that's my function. But I could be thinking of a different function, this same rule or relation here, but I could just be looking at x member of the integers. That would be a different function. So again, this concept of a function is very general, but you have to be very specific about it. You need to know what the domain is. Now, when we start doing some work, we're going to be very squishy here. We're not going to always mention the domain. Sometimes we'll ask, well, what could the domain be? Meaning, we'll look at the real numbers and we'll say, well, maybe some real numbers aren't going to work, so they're not going to be part of the domain. All right. There's this other view, again, we'll see here, this idea of a function. There's the f being like a factory, but, again, it's going to include the domain. What are the raw materials I can put into the factory? And then we'll take, for each material we bring into the factory, what is the output? Since I know a lot of you are interested in computer science, I want to make a a little side note. In computer science programming languages, we also have the term function, which is very similar. We'll have some routine f of x. They look the same way. And what this is we have some code here. And at the end of it, we'll have a statement that says return something. So this is just a piece of code that you give it a number and it returns a number. Very similar to the math idea, but again, this is just operating on what you give it. Right? When we talk about a mathematical function, we're talking about, the mapping, the domain, and all the things that, where each member of the domain is mapped to. So it's a little different terminology, although for practical purposes, it's, you could use them almost interchangeably. Okay, so again, we have a set domain we're going to call A, and we're going to use this function to get an output to some set B. If we have a specific value of x, some x0, this is going to get mapped to f of x0, some specific number, like 1 mapped to 1 or 2 mapped to 4. And we have a name for this. This is called the image of x0. I'm writing it all out. We might not write the whole thing out under f. We're looking at the function f. We can say the image is x0. If we look at all the images, as we take the domain, we plug each element into the function. See, this set, this is just what we could get. But if we just look at the subset of B, which is all these images that come from A, we have what's called the range of F. And we can define that as the set of F of X, where X is just some member of A. Right? This is a set, and it's a subset of the set B that our function sends things to. Just a side note, pretty much all the functions we're going to deal with are going to have numerical inputs and numerical outputs. But that's not a requirement in mathematics. We'll see later, functions can actually have multiple inputs. So I could have some function, I'm going to call it t of x, y, and z, right, where x, y, and z are numbers. But the output could be a triangle with sides, length, x, y, and z. The inputs and the outputs don't have to be numbers. It's just what we're going to see in this class. All right. Okay. Some more terminology you've probably seen before. x here is a variable, right? It's just some member of A that we're going to plug into F. And we'll call this, you've probably seen this terminology before, the independent variable. That's the variable you pick. The output, which is this value f of x, this is sometimes called the dependent variable. Okay. With a note, A and B can and often are the same set. For example, A and B could be each be all real numbers. A little later in this section, we're going to look at a function called this is a notation. It's double square brackets, and it means let's see how to say this. The words are, not coming to me, but x is, bracket bracket x is x that is an integer. Right, that bracket bracket x is an integer less than x, less than or equal to x. I'm not doing this very well today. I shouldn't go off my path. This is the integer which is less than or equal to x. It's the greatest integer less than or equal to x. So what do I mean by that? F of 1 would equal 1, but f of 2 would equal 1. Oh. F of 1.5 would equal 1. F of 1.99 would equal 1, but f of 2 would equal 2. So the whole point in doing this is the dependent variable, or the domain of this, is a real number, but the range is just going to be made up of integers. So these don't have to be the same set. Could be. Right, a little bit on notation. Most commonly, you will see me write something like f of x. X is the most common letter I'm going to use for the independent variable. And f of x, f, is most commonly how I'm going to express a function. But you will see other things. I could just as well say f of y or f of t. If I say f of t, usually it's t has something to do with time. I might need to use different names because I'm dealing with more than one function. So I'll probably just start incrementing here. I might use g of h, g of x, h of x. And when I get further than this, then I'm going to have to be more creative. I might use a letter that expresses what we're talking about. If something were a height function, I might say capital H of x. You're just going to see this in different ways. All right, this is very abstract. In some ways it's simple, but you know, get your head all the way around it may take a little while. Are there any questions so far? Has anyone seen functions before? Okay, a few people. All right. All right. Let's look at some different ways that we might see a function described, or more specifically, the rule that a function uses to do the mapping. The simplest way would be just with a table. So the table might look like this. I have x and then f of x here. And I might have a set of values. 1 goes to 3, 2 goes to 9, 3 goes to 27. That would be one way to express this. You might think that my function here is 3 to the x. That would be fine for these three members here. But or it might be -1. So when you don't have some very clear way to describe the mapping, you can always use a list. Just a list, a table. We could use a table in a different way. This could be f of x, f of x, and let's say we were using a function to describe the cost to send a letter, right? So this might be over x might be the weight in ounces, and this might be the price in dollars. And we could say less than equal to 1 ounce. Well, today that's 49 cents. Today, tomorrow, something bigger probably. Greater than 1 ounce and less than or equal to 2, that would be 70 cents. And so forth. Greater than 2, less than or equal to 3 would be 91 cents. This is a different way to express a function. We can go back to kind of our functional way of describing this. We could write this like this. We could say f of x, we will. Put a big curly bracket here, and then just say, all right, f of x is equal to 49 cents if x is less than or equal to 1. 70 cents, x is between 1 and 2, and 91 cents, 3. We have a name for this. This is we call it piecewise function. That's just a name we attach. There's nothing special about it. It's just a mapping, but it's easiest to describe it in pieces. So that's a second way we would describe a function. Third way, and And the most common way we're going to use in class is to just use an algebraic expression. I think it's time to refill this. See how this works. Algebraic expression. We've already seen, you know, f of x could be x squared or some other polynomial. We might write something a little more descriptive. We could say the area of a circle. The independent variable would be the radius, and that would be, of course, pi r squared. That would be an algebraic expression. Let me ask a question about this. Given I give you this function, the area of a circle, so forth, what's the domain? What's the domain? What can R be a member of? What's the domain of this function? Let's think about that for a second. Anyone? I'm just saying, if I gave this to you on an exam and said, what's the domain of this function? What values could R take? Yeah.
All real numbers.
Okay, it's a good start. But there's a problem. Yeah.
Is it all numbers greater than 0?
Yeah, it's going to be reals greater than 0 because there are no negative radii, right? We try and develop a weird geometry where you have negative radii, negative lengths of lines. I'm not sure what that would be. But yeah, R is greater than 0. The circle had radius 0. What would that be? Be like a point, right? Center. We actually have a name for that. Called a point, a degenerate circle. Degenerate's a good math term. Shows up now and then. It just describes something which fits the definition, right? And what's the definition of a circle? You got a center and a radius. But radius 0, you know, it's not quite what you mean. Okay. Just a side note there. All right. One more way we could describe a function. We could use a graph. So let's say I say that f of x equals the square root of x. Okay, and 0, that's 0. 1, that's 1. 4, that's 2. So there's my graph of the square root of x. Here again, the independent variable is x. And we do this so often, you know, that sometimes we kind of mix up the terminology, right? We can say y equals the square root of x. Well, I'm kind of referring to a graph, right, where y is this dependent variable. But this is a function, too. If you try to represent this by a listing, like I had before, you would have a problem because you couldn't really list everything, right? Here I've got an infinite number of members of my domain. So in that case, either drawing a graph or just writing it as f of x equals square root of x would be a better way to represent it. Just revisit for a second this idea of a piecewise. We will be seeing a piecewise function a lot. If I have some function, I'm going to use c because thinking of the cost of something, right? And the cost is 39 for 0 between x and 2. And it's 39 plus 15 times x minus 2 or x greater than 2. Okay. So this is like the cost of something where there's a minimum price. Like let's say your phone, right? You pay some minimum each month, right? Let's say $39. But then if you actually use your phone, well, the first 2, whatever, hours or minutes you get with your $39, but thereafter you're going to be paying for it. So this can be very useful in economics. Let's take a look at the graph here. I guess there's 39, right? That's where we're going to start. My axes are going to be a little odd here. 2, 3, 4. This 40 is right there. So between 0 and 2, I'm at 39. And then I don't know quite what the slope 15 would look like. It would kind of look like that from there on. It shouldn't be, given your background in graphing and algebra, it shouldn't be too hard to go between these two. If you see a graph like this, you ought to be able to write the piecewise function. If you see the piecewise function, you should be able to come up with a graph. Okay. Leave the 2 functions up here for a minute. One of the things we're going to need to know how to do is to evaluate a function at some value. Pretty straightforward. If I said, what is C of 5? Well, for a piecewise function, we take a look and say, well, no, x isn't between 0 and 2. X is greater than 2. So we're going to use this algebraic expression, 39 plus 15 times 5 minus 2. That's 3. 3 times 15 is 45. 45 plus 39 is 64. It's pretty straightforward. We said, what's f of 16? You all should know that before. We said f of 5. Well, this would be a place a calculator would be really handy, right? You know the square root of 4 is 2. The square root of 9 is 3, so we know it's going to be between 2 and 3. And we could approximate, or we could hit that button on the calculator. More typically, we might have a function like this, quadratic, or that would be a parabola. And we have some value, say f of 2. And again, we can just substitute for x here 2. And when we get 6 plus 2 is 8, minus 5 is 3. So f of 2, f of x at 2, or f of 2 would just be 3. Oh, except I meant squared, didn't I? So I got that wrong. 12 plus 2 is 14 minus 5. Good so far? It's, some of you have seen this before, so it seems straightforward. Let's take a look again at the domain of a function. Earlier in the class, we looked at the domain of an algebraic expression, and we're pretty much going to use that same basic knowledge. I say f of x is equal to 1 over x times x minus 1. So what's the domain of this? Well, again, since I haven't told you it's the rationals or the integers, you can assume it's the maximal set that includes the real numbers, but of course not all the real numbers, right? So this is a number of the reals, but what else do we have to say here? Yes?
Not equal to 0.
X is not equal to 0. Okay, good. Anything else? Yeah?
X can't equal 1.
X isn't equal to 1. That's because this function would not be defined for x equals 0 or 1. All right, that was pretty straightforward. Let's try something a little trickier. So g of x equals the square root of 9 minus x squared. What would the domain be here? Again, let's start with x as a real. Yes?
X isn't equal to a number greater than 3.
X is never greater than 3, so it's
Is less than.
less than 3. Okay. Good start. Anything else? What about x equal to 3?
It
9 minus 3.
because then it'd just be 0.
Hmm?
I said it can be 3.
It could be, yeah, so it could be
So
less than 3. Anything else? What about negative 5? That's less than 3, right? Square root of 9 minus negative 5 squared is...
It's less than greater than negative 3. This x has to be greater than negative equal to greater than 3.
Yeah. Or, if you like, you could just say
Plus or minus.
absolute value of x is less than 3. How about that? All right. Let's do one more for each of t. T over the square root of t plus 1. Okay, what would the domain of this be? Again, t is a member of the reals, and what else? Yes, Carlos?
It can't be -1?
Sure can't be -1, so that would be 0. Just a chance to get started on the homework here, right? Because you're going to have to do something like this on the homework, right? What other values of the reals are not going to work? They're going to be undefined here.
Greater than 0?
Well, let's just look at that for a second. T greater than 0. How about -1/2? That would work, wouldn't it? That would be the square root of a half. So, I know where you're going with this, but you got to be a little more precise. Yes, Ian?
It can't be equal to 0?
Sure it can. The square root of 0 plus 1 is 1 over 0 over that, it's just 0.
It can't be less than -1. Because it
So t is
cannot be.
not less than -1.
So you get the -2 plus 1.
So that means t is greater than or equal to 1. Is that right? Is it not less than, I'm sorry, greater than or equal to -1? Is that right?
Yeah.
Yeah, that sounds good. Let me just suggest a way to look at this. We know that t plus 1 has to be greater than or equal to 0, right? Because what's under the square root sign has to be 0 or positive. Although 0 wouldn't really work, would it? Right? So really we want greater than 0. So that just becomes t is greater than -1. So this is now redundant. I don't really need that. Okay, so the domain here is just t is a real, but greater than -1. Digress for a second. So, I'm thinking something and then I'm thinking I'm wrong. Thinking, gee, when I was younger, I probably didn't forget things quite as much. And then I was remembering the time I forgot to go to class when there was an exam. Well, I didn't forget, I just didn't wake up at the time. But it does get a little harder, and so far I've forgotten my keys one day. It's all right. Forgot the camera one day. Forgot to turn on the camera one day. Today I forgot my coffee. Really sad. It's really coffee. It's not whatever you were thinking, whiskey or it wasn't water either. Okay. My digression is over. I searched my notes. Okay. Let's look at graphing functions for a minute. This is going to be something we're going to do a lot. Somebody here whose retina does not see blue, is there? I've run out of black.
I think it's over.
You sure you want to volunteer it for this purpose?
Yeah, that's fine.
All right. Thank you. Okay. To be very mathematically correct, the book defines the graph of a function this way. By graph here, we're not meaning like the xy axis and the plane, we mean the points on that plane that represent our function. And the book defines a graph as those points x, comma, f of x, right? It's an ordered pair, such that x is a member of the A set, which is the domain. Probably better to use D here, but that's what the book uses. This is a pretty tortured way to describe it, but graphs are really good because they give you a visual idea of what's going on. To graph something, you could use a table. And I know I'm going to be repeating myself here, but let's look at x and f of x equals square root of x. So we could plot some points. 0 goes to 0, 1 goes to 1. Some nice points that we can calculate easily. 9 goes to 3. And then we could draw our graph. 0, 1, 1, 2, so forth. And that would be our graph of this function. Not all graphs are functions, however. Let's take a look at something you're no doubt familiar with. Let's say x squared plus y squared equals 1. That would be what? It would be a circle, radius 1. But this is not the graph of a function, because if I look at some value, say a half, there are going to be 2 points on the graph in the y-axis that are represented by that. Square root of half, square root of minus a half. So we have a rule of thumb, we'll call it, even though there are no thumbs involved, called the vertical line test. The vertical line test says if you have a graph, you draw all possible vertical lines, and if they just intersect one point, you have function. But if even one of these vertical lines intersects 2 points, it's not a function. That's not to say that you couldn't find a way to make this sort of into a function. You could say f of x equals, and I'm going to be very specific here, the positive square root of x squared minus 1. X squared minus 1? Yeah. Right? If I solve for y here, right, y equals 1 minus x squared, so y equals square root of 1 minus x. And I say my domain is just x between minus 1 and 1. Well, now my graph looks like this. Now my graph passes the vertical line test. And in fact, it's now a graph of the function. So sometimes you have something, you want it to be a function, but it's not, because it returns more than your value. But you can restrict the domain in such a way that you get a function. I think that's enough for today. Today's Wednesday? Wednesday? Yeah, Friday I have some additional things to show you, but I'll need to bring up the computer and I don't